Hello everyone. We're going to start on Module 11 with Section 11.1 on the dissolution process. To start with, Module 11 is about solutions. So Module 9 was about gases, Module 10 was about liquids and solids, Module 11 is about solutions. So all of these modules are about basically physical states. This is the only one that is about a physical state where we're focusing on the fact that it is in fact a mixture. So hopefully you can see some of the commonalities in these three modules, and in fact this particular section of Module 11 will hopefully focus on some of those ideas. So the learning objectives here describe the basic properties of solutions and how they form, predict whether a given mixture will yield a solution based on molecular properties of its components, and explain why some solutions either produce or absorb heat when they form. So we've already talked about the idea of a solution as a mixture of things in which the mixing is occurring on the level of the molecules. So when we look at it, we can't actually tell anything different about it compared to say element or compound. They would look the same. We would have to know more information to know that they are solutions because of the level where the mixing is occurring. In a solution, there are more than one component. Whichever component has the greatest concentration is called the solvent. So you'll want to remember that. And then anything other than the solvent is referred to as a solute. So just remember those terms and what they mean. We'll often be talking about the amount of a solvent or the amount of a solute or the amount of a solution in this chapter, so you need to know which of those we're referring to. We're showing here an example of something dissolving, how we could write that as a chemical, kind of in the form of a chemical reaction. It's not technically a chemical reaction, but we're kind of showing it that way, where we're showing the solid, and then most of the solutions we'll look at, not all solutions, but most of them will be solutions in water. And we show that with this AQ, which means aqueous, which is a solution in which water is a solvent, so dissolved in water. So we'll see a lot of those, but those are not the only thing that happens. We're showing another example here of a solution, and you'll notice that something is different going on here. Whereas this one we're showing it all together, here we're showing it as being separate. This is something, the difference between what's going on here and here is something we'll explore in more detail in an upcoming section of this module. There are lots of solutions that can form, and we're showing some different types down here. And what I want you to recognize here is that you can have a solution that is in any physical state. And the solvent could be any physical state, so we can see gas, liquid, solid for the solvent. And the solute can also be in any physical state. The solution itself will be the physical state of the solvent, but something could dissolve into the solvent that would normally be a different physical state under those conditions. A great example of that would be a soft drink where you have carbon dioxide dissolved in water. When the bubbles form in the soft drink, that is no longer a solution when you see the bubble, but before you see the bubbles, that carbon dioxide is actually already there. One type of solution is an alloy. Alloys are solid solutions of metals. And to create an alloy, you don't actually make it in the solid state. It has to be, the metals have to be, first of all, melted, so they're liquid. So you can have mixing occur at the I guess atomic level in this case if they're metals. Just be aware there are different possibilities of solutions, even though the rest of this chapter The rest of this module will be mainly focusing on solutions where water is the solvent. So just to kind of summarize some of the traits that are present in any solution, they are homogeneous. They have the same composition throughout the solution. So you don't have chunks in one part that are different than chunks in another part. The physical state of the solution is the same throughout. The dispersion within the solution of solute and solvent is occurring at the molecular level. And so you have either molecules, atoms, or ions that are mixed with molecules, atoms, or ions of other substances. Whatever is dissolved is present in the solution. It does not separate from the solvent and fall to the bottom. If that's happening, there is something else going on there. And then the composition can be varied. We can change the composition of the solution by having different concentrations. And that's something we've kind of addressed in an earlier module. And we've used the molarity concept, for example, to describe aqueous solutions and measuring concentration for them. Let's talk a little bit about how a solution forms. The formation of a solution is what we call a spontaneous process, and the idea of spontaneity is something that's discussed in greater detail in Chemistry 1B, but it's basically something that follows these two guidelines. So it has to be a combination of these two. And it's something that happens. So when we use the word spontaneous in chemistry, we mean it's going to happen, not how fast it's going to happen, but it's just things happen in that direction. So one is the decrease in internal energy, and the other is an increased dispersion of the matter in the system. And that idea is called entropy. Again, we'll talk about that in greater detail in Chemistry 1B. But these two things together lead to spontaneity. You could have maybe some of number one and maybe not number two, or vice versa. But you have to have some of this in order for the solution to form. Your book discusses this idea of an ideal solution, and just to be clear, unlike an ideal gas, we don't really have ideal solutions unless you're thinking specifically of a gas. In terms of the way this book is defining it, there are other books that might define ideal solution a little bit differently than is being defined here. But the idea is you can completely ignore any intermolecular forces, and we know we can't actually do that. So let's look at what actually does happen when a solution forms. So when a solution forms, you have solute particles and solute and solvent particles that are brought together. And when that happens, you have this mixing going on where you have molecules of one, molecules of the other, and they're all kind of mixed together. We can think of this process as different kind of thermodynamic steps. So think back to Module 5 when we looked at maybe there's different ways of representing a chemical reaction by breaking apart your reactants and putting them back together as your product. So that's basically what we're talking about here. So there's a few things that are happening when this is going on. So for the solute, there are intermolecular forces that favor the solute particles being together. So one thing we have to do is we have to break those forces. We have to separate them from each other. So that's what we're showing here. The expanded solute is we're saying, okay, we're basically taking the solute and turning it into a gas. And then we're doing the same thing for the solvent. We're taking the solvent and turning it into a gas. Now, are we actually doing that when we make a solution? We're not. This is basically a thought experiment using thermodynamics to keep track of everything that's going on. Both of these require energy, right? So it's energetically favorable for them to be close together because of kind of their intermolecular forces, their tendency to stick together. The third step that we're showing here is we are putting them back together. So we're taking the solute and solvent, combining them. And what can happen here is you can have intermolecular forces that make that favorable. It could be a reversal of kind of what already happened. In order for that to be true, though, you have to look at, do they have similar intermolecular forces? So if their intermolecular forces are similar, then this will be favorable. If they have different types of intermolecular forces, then this will not be favorable. For example, if your solute is something that is nonpolar, breaking it apart does not require a whole lot of energy. And breaking apart your solvent does require a whole lot of energy. So if this is water, it takes a lot of energy to break apart all those water molecules and turn them into a gas. And then when you put that all back together down here, you're forming these intermolecular forces between the water and this nonpolar substance, and they're not going to be very strong, and they won't be strong enough to overcome the fact that you needed to have a lot to break that water apart in the first place. What that means is that if there is a difference between the solute and the solvent, they might not form a solution very well. And that difference we're talking about is based on similarities in the intermolecular forces between the particles. So if the intermolecular forces between the particles are not similar, you might not get a solution. So there's a discussion here about some of those ideas. And I'm trying to see if they talk about it here. Most textbooks talk about it somewhere in here. But the rule of thumb we have for this process is like dissolves like. The idea here being the like is similar in terms of intermolecular forces. Things that have similar intermolecular forces will go well together. Things that have different intermolecular forces will not go well together. So one of the things you want to be able to do is decide which things will form some solutions when mixed together. So there is some discussion here in your book about that in terms of the types of interactions that do form solutions. One of the things I will note here is that if you think back to Module 4, we had our solubility rules. Some of the forces here are stronger, maybe for the solute than for the solvent, and that's why some of those will not be soluble. But that level of solubility in terms of ionic compounds is fairly complicated to understand, which is why for now we're using solubility rules instead of trying to figure out, well, why is silver chloride insoluble, but calcium chloride is not. So we don't need to know that. We use solubility rules for that. So that is it for section 11.1.